So in this next system, you'll notice that both of our equations are nonlinear. They both involve exponents, but more importantly, their terms line up in that we have an x squared term and a y squared term to where the process of addition or elimination is actually usable here. So let's take a look at how that would look. With elimination, we know we want one of our pairs of variables to have the same coefficients but opposite signs. So easily enough, we could take one of these positive y squareds and convert it into a negative y squared, and we'd be good to go. So I will take the second equation. I'll leave the first one alone. For the second equation, if I multiply everything by a -1, that'll give me negative x squared, negative y squared, and that equals -10. And then with the addition method, that very quickly simplifies down to 3x squared equals 3, with those y squareds canceling. Dividing both sides by 3 gives me 1, and then we use a thing called the square root property, where we take the square root of both sides, and we have to remember that when we do so, we get a plus or minus on this value. Conveniently, the square root of 1 is 1, so we get x equals plus or minus 1, meaning we've got x equals 1 and x equals -1 as our possible solutions. We can then take those equations, or those solutions, and substitute them back into either equation. I'll go to the second one, slightly simpler looking. So for the x squared plus y squared equals 10, starting with the x equals 1, that'll be 1 squared plus y squared equals 10. So 1 plus y squared equals 10. Subtract the 1, and we get another place where we will do another square root property, giving us y equals plus or minus 3. And then let's go ahead and look at the other one. Let's look at x equals -1. In the same equation, -1 squared plus y squared equals 10. And it looks like it results in the same thing. We get another y squared equals 9, square root property, y equals plus or minus 3 again. And notice each of these plus or minuses is paired with the value of x. So what we have here is the x of 1 paired with the y of 3 and -3. So 1, 3, and 1, -3, along with the x of -1 paired with each of those y values. So -1, 3, and -1, -3, and we actually end up with 4 different solutions. Now, as it currently stands, we've not discussed this shape specifically here. This is our basic form of a circle for an equation. We will get into this later on, so we can't really describe the picture necessarily, but it does make sense here that we actually have these 4 different solutions to the system. Now, lastly, we look at a system here where they are again both nonlinear equations. The terms don't match up perfectly though. Notice we got x squareds, but here is a y and here's a y squared. Well, notice with the addition method, it could still work if we were to do the addition method and specifically use it to eliminate the x squareds. Then what would remain is things that involve either constants or y. So we can do the elimination on this approach or this system, even though it doesn't quite look like what we're familiar with doing elimination on. We just need to make sure these x squareds are on the same side of the equal sign and, as usual, have the same number but opposite sign for coefficient. And so since this x squared's on the right, this x squared's on the left, if I move him over here, so again, I'll leave this first equation as it is, x squared on the right-hand side, but if I subtract the x squared over, that leaves y squared on the left. Bringing him over makes that a -x squared, and then there's a +9 there. All that matters is these are on the same side of the equal sign, and they've got that same number opposite sign for coefficient. When we say we add down, the difference is these don't add together, they just are 2 separate terms, right? Y squared plus y. Here, the x squareds cancel, and we're left with that 12 over there. And now with this equation being in terms of one variable, it's looking like a pretty simple quadratic. We can just move that 12 over to the other side to create our equation, and then 2 numbers that multiply to -12 but add to +1 would be a +4 and a -3, giving us y plus 4 equals 0, and y minus 3 equals 0. So y equals negative 4, and y equals 3. All right, now from here, let's talk again about this system. This system is what we can recognize as a parabola and a circle. So again, thinking about how parabolas and circles could intersect. Not that this is the way they intersect, but you could have, there's actually a couple different ways. You could have a parabola and a circle that don't intersect at all. You could have a parabola and a circle that have 1 point in common. You have a parabola and a circle that have 2 points in common. You could have a parabola and circle that have 3 points in common, right? 1, 2, 3. Or you could have a parabola and circle, oops, wrong circle bigger here, that have 4 points in common. So we're not sure which of these that we've got. So with that being said, we notice that the parabola is the more restrictive of the two equations. If we can look at where we have this equation, right, solve for at our y values, we'll be looking at the points that are on the parabola, not, again, like I pointed out in the other video, finding some values that actually have other values on the circle that aren't points of intersection. So with that being said, we'll take these values and plug them into our parabola function. So our parabola function was y equals x squared plus 3. So plugging in the negative 4, we'll start with checking solutions for that. So for negative 4, negative 4 equals x squared plus 3. Subtracting the 3 gives me negative 7. And right there, I'm seeing x squared equals negative 7, or if I thought about the square root property, we'd realize that that is going to lead to imaginary, right, non-real solutions. So if that's the case, we're not going to see any points from that. We can't graph imaginary numbers on our real axes, so that led to values that we cannot have for x. So let's check y equals positive 3. So that's 3 equals x squared plus 3. Subtracting gives me 0. Square root property gives me 0. So this 3 pairing with this 0, y pairing with that x, that looks like that's the only point of intersection. Meaning we essentially had a scenario, something like this, where we had our circle and our parabola with that 1 point in common. But again, based on those pictures we drew, we could have had none, 1, 2, 3, or even 4, depending on the exact orientation of these two graphs.